All right, how the heart is controlled and stimulated. So we want to focus on identifying and locating the components of the heart's conduction system and compare and contrast the parasympathetic and sympathetic innervation to the heart. So the heart's conduction system is going to initiate and conduct electrical events to ensure proper timing of contractions. So remember that our heart needs to be contracting in time or in rhythm with each other. So there's specialized cardiac muscle cells that have action potentials but do not contract, and its activity is influenced by the autonomic nervous system. So also we can think of it as the automatic, the one that we're not necessarily thinking about. So here are some of the conduction systems that we have. We have the sinoatrial node, or the SA node, which initiates the heartbeat. We also can think of this as our pacemaker. It's located high in the posterior wall of the right atrium, so on the back side of the right atrium. The atrioventricular, or AV node, is located in the floor of the right atrium near the right AV valve. Then we have our atrioventricular bundle, also known as the bundle of His, and it extends from the AV node through the interventricular septum, and it divides into left and right bundles. So again, interventricular septum separating the right and left sides of the right and left ventricle. Then we have the Purkinje fibers, which are going to extend from the left and right bundles of the bundle of His to the heart's apex, right, that end piece, and they're going to course through the walls of the ventricles. So we can see here a good image that shows us these different pieces, right? Our SA node starting at the top here, the pacemaker, and then we have our atrioventricular node right above the tricuspid valve before getting into the right ventricle. Then we have the atrioventricular bundle, or the bundle of His, that's going to be coming down this direction. We have the right and left bundles that are going to split here, and then the Purkinje fibers are coming up in to each of these places. I should use a different color. Here we go. Coming into these different pieces here, connecting into the papillae muscles and the rugae that are in here. So, all right, so the cardiac center is found in the medulla oblongata. It's going to contain cardioacceleratory and cardioinhibitory centers, so things that are going to speed up the heart and things that are going to slow it down. So we receive signals from baroreceptors and chemoreceptors in the cardiovascular system within the cardiac center, and then it's going to send signals via the sympathetic and parasympathetic pathways of the nervous system, and it's going to modify, not initiate, the cardiac activity. So it'll just influence the rate and force of the heart's contractions. So there's the parasympathetic innervation that decreases our heart rate. So parasympathetic is going to decrease the heart rate, and it's going to start at the medulla's cardioinhibitory center, which makes sense, inhibiting the heart rate. It's relayed via the vagus nerves, or the CNX here. The right vagus innervates the SA node, and the left vagus innervates the AV node. We have the sympathetic innervation, which increases the heart rate and the force of contraction. So parasympathetic is the decrease, and the sympathetic is going to be the increase. It starts at the medulla's cardioacceleratory center, again making sense, relayed via the neurons from T1 through T5 segments of the spinal cord, and it extends to the SA node, the AV node, the myocardium, and the coronary arteries, and it increases the coronary vessel dilation. So we can see here just an example of how it's innervating the heart, so through the vagus nerve, and then also right into connecting with the SA node, the AV node right here, and then into the coronary arteries and the myocardium. All right, so some questions for us. Which of the two autonomic nervous system divisions have an effect on the force of the heart contraction? Of course, that's going to be the sympathetic innervation and the parasympathetic. And then we have what is the cardioinhibitory center and where is it located? It's a part of this parasympathetic division that innervates the heart to decrease heart rate, and it's found in the medulla oblongata. All right, so stimulation of the heart. Heart is contracting in two events. So the conduction system that initiates and propagates an action potential. And then we have the cardiac muscle cells are going to be firing action potentials and contracting. So this process happens first in the atria, and then it's going to move to the ventricles. So we just have some pictures here kind of showing us how that action potential is going to move down. Muscle contraction, same deal that we've seen in skeletal muscle, how it's going to go ahead and be elongated and then shorten. The sarcomeres are going to shorten, causing a contraction in the heart. So to the nodal cells at rest, nodal cells in the SA node initiate the heartbeat, and they're spontaneously going to depolarize and generate an action potential. So the resting membrane potential typically is about -60 millivolts, but these cells do not have a stable resting membrane potential. So many are going to have common membrane proteins. So we've got our sodium and potassium pumps, our calcium pumps, and our leak channels. They also have specific voltage gated channels. So we have our slow voltage gated sodium channels, our fast voltage gated calcium channels, and then our voltage gated potassium channels. So we can see those here, all those different channels, our calcium, our potassium, and our sodium. And notice the nodal cell is a lot different looking than our skeletal or our cardiac muscle cells. So the SA node cells exhibit what's called autorhythmicity or spontaneous firing. So first thing that they're going to do is they're going to reach a threshold. So slow voltage gated sodium channels are going to open and sodium is going to flow into the cell. The membrane potential is going to change then from being a -60 millivolts to a -40 millivolts. This is what we call the threshold value. Depolarization of the action potential is our next step. So we're going to have our fast voltage gated calcium channels are going to open and calcium is going to flow in. So we're going to have even more positive charges coming in. So then our membrane potential is going to change from -40 millivolts to just above 0 millivolts. So notice that we've dropped dramatically and become super positive versus being very negative. So then we're going to have our next step, which is repolarization. The calcium channels are going to close, stopping the calcium from coming in, and then voltage gated potassium channels are going to open, so potassium flows out of the cell because note we're going to have a lot of potassium in there and it's going to flow out. The membrane potential is then going to go back to its rest value. It's actually by the passing of those potassium channels is going to allow it to come back to -60 millivolts. And the voltage gated sodium channels are also going to open at -60 millivolts, and then the process is just going to go ahead and begin again, right? So we're just cyclically coming back here to go ahead and reach that threshold to drop it down to -40 millivolts, going ahead and opening the calcium channels to then drop to 0, and then closing those and allowing the potassium to flow out to bring it back up to -60 millivolts. So at rest, one SA node action potential starts about 0.8 seconds after the last. So this is going to translate for us to about 75 heartbeats per minute. That's kind of the quote-unquote normal. So inherently, the SA node would fire faster at 100 per minute. This is seen in heart tissue cultures. And in the body, we have what's called a vagal tone, so parasympathetic activity relayed by the vagus nerve, and it keeps resting heart rate slower than what we typically see in that heart tissue culture of 100 beats per minute. So this is just showing us those 3 steps where we're going ahead and reaching our thresholds. Those calcium channels are opening, we're reaching that 0 millivolts, and then going ahead and having the potassium channels open to bring us back down to a -60 millivolts. So again, about 0.8 seconds, translating into 75 beats per minute. And then this is just another visualization showing us here, you know, the change in the sodium channels opening, coming into the cell, changing into that -40 millivolts. And then our next step of full depolarization, that's going to trigger those calcium channels to open to bring us down all the way to 0 millivolts or positive millivolts. And then we're going to have that repolarization of our calcium channels opening and allowing the excuse me, not calcium, the potassium channels to open and allow the potassium to go out so that it brings us back down to that -40 to -60 millivolts. All right, so a little comparison of our nodal cells and neurons. The similarity between them is that both can fire action potentials, but the differences are that neurons require stimulation to fire, but nodal cells don't. So they're just, again, they're in that cyclical firing system where they're just going and going and going. Nodal cells also are not going to have a stable RMP. They exhibit a pacemaker potential when their sodium channels are open. And in neurons, the action potential depolarization is from sodium entry. In nodal cells, it's actually from calcium 2 entry. So notice that the sodium just goes ahead and gets it to the threshold, and then calcium is actually going to be the one that depolarizes it, and then potassium is going to come in to repolarize. So the conduction system of the heart, we're thinking of the spread of the action potential. That's what we're going to talk about next. So after starting at the SA node, the action potential is going to spread. So it's going to distribute through the atria, and it's going to reach the AV node right there at the cusp, or at the tricuspid valve. So excitation travels via the gap junctions, and the two atria contract together. So notice that it's the two atria that are going to contract together at the top, not the two bottom parts, right? So the action potential is then delayed at the AV node, which again, we talked about the fibrous skeleton of the heart, super important for insulating so that the ventricles don't contract at the same time. The AV nodal cells are also slow because they have a really small diameter and a few gap junctions, and this also increases the insulation, right, and allows it so it's not going to go as quickly. It's also going to hit the fibrous skeleton, so there's kind of only one path, and it's a bottleneck, and it allows the ventricles to fill before they're going to contract. So then the action potential, once it's kind of hung out there at the AV node for a minute, it's going to travel through the AV bundle, or the bundle of His, to the Purkinje fibers. And then that action potential is just going to spread throughout the ventricles. The gap junctions are going to allow the impulse to spread super quickly through the cardiac muscle fibers, and the cells of the two ventricles are going to contract basically at the same time. So we can just see right here at the top, coming from the SA node to the AV node, it's going to take a little break, and then it's going to continue on down through the fibers in the bundle of His. All right, so there's some specialized features that are associated with the ventricles. The Purkinje fibers are larger in diameter than other cardiac fibers. The action potential is really, really fast, extremely rapid. It ensures the ventricles are going to contract at the same time because they have to. The papillary muscles are stimulated to contract immediately. So the muscles anchor the chordae tendineae of the AV cusps, so that ensures that it pulls on cusps just prior to increase in pressure in the ventricles to close the things. So then stimulation begins at the heart apex, like we talked before, and ensures the blood is efficiently ejected toward the arterial trunks, again, moving it upwards. So a little bit of a clinical view, we have ectopic pacemaker. So a pacemaker other than the SA node. So the conduction system cells are going to be found other than in the SA node. They also have the ability to spontaneously depolarize. They depolarize at slower rates than the SA node. The AV node is the default pacemaker if the SA node is impaired. So the AV node with an inherent rhythm of 40 to 50 beats per minute versus that 75 in our body. But it's fast enough to sustain life. So cardiac muscle with a rate of 20 to 40 beats per minute is usually too slow to sustain life. Like, you're going to die. You don't have enough oxygen to all your cells. All right, so looking at our check for understanding, what ionic event creates the depolarization phase of an SA nodal cell's action potential? So note that that's going to be that calcium rushing into the cell. And then what is the functional significance of the small size of the AV node cells? That's just super important. So it slows down the process of that action potential moving into the ventricles so that the ventricles can fill with blood and then go ahead and pump and contract and allow the rest of the blood to flow into the pulmonary system and the systemic system.